Hi, this is TW Huang. Today we are going to understand Executor in Taskflow. This is the takeaway for today's presentation. We are going to learn the basic usage of the Taskflow Executor and understand how we can perform cooperative execution within the Executor. Then, we will learn how to observe and customize worker behavior in the Executor. Finally, I will conclude the talk. A TF executor manages a set of working threads to run submitted tasks. The core scheduler implemented a work staging algorithm to achieve dynamic load balancing, as well as a notification algorithm that can adapt worker availability to dynamically generated task parallelism. You can specify the number of workers when creating an executor. The constructor of TF executor takes an unsigned integer to spawn n workers. For example, here I create an executor of 4 working threads. If you do not specify the number, Taskflow will simply use the number equal to the maximum hardware concurrency available on your machine, which often goes to the number of available CPU cores. It is very important to understand that creating an executor is not free because it involves non-trivial overhead like spawning threads, setting up the work staging data structure, and so on and so forth. Unless you really need multiple executors, the best practice is always to just create one executor in your application and reuse it as much as possible. For example, in C++, you can create a global executor using an inline variable. After you define a task graph, you can submit it to the executor for execution. Execution methods are either blocking or non-blocking. Blocking methods will wait for all tasks to finish before returning, while non-blocking method return immediately. You can use different run functions to submit a task flow for execution, whether to run it once, multiple times, or repeatedly until the given condition is met. When you submit a task flow for execution using the run functions, you get a TF future, which is derived from standard future, with a few task flow specific operations added, such as cancellation and so on and so forth. Then, you can use future.wait to block until that task flow finishes, or executor.wait for all to block until all submitted tasks finish. When you submit a task flow to the executor using the run functions, the executor returns a TF future object that holds the result of that execution. As mentioned earlier, TF future is derived from standard future. In addition to the standard future functions, you can call cancel to stop a running task flow. The example below shows how to cancel a submission of the task flow of 1000 tasks. Notice that the cancellation is non-deterministic. Requesting a cancellation does not guarantee that a running task flow will stop immediately. Depending on the scheduler, the cancellation may or may not take effect. Each call to the run function is an independent submission called topology. A topology is an internal data structure that the executor creates to handle a submission. A submission can be a single run, multiple runs, or a run until execution. For example, the code below submits taskflow 1 3 times, with the first time running it once, the second time running it 10 times, and the third time running it until I is bigger than 5. Then it submits taskflow 2 1 times. As you can see, you can submit the same taskflow multiple times, and multiple submissions of the same task flow will be executed sequentially. In this example, this basically means future 1 will become ready before future 2, and then future 3, and so on and so forth. However, when different task flows are submitted simultaneously, there is no guarantee which submission will finish first. In the same example here, even if we submit task flow 2 after task flow 1, task flow 2 may still become ready earlier than the completion of task flow 1. In other words, future 4 may become ready before future 1, future 2, or future 3. A key aspect of the executor is that it does not assume any ownership of a graph. Every task belongs to a graph at the time and remains alive with that graph. In other words, as long as the task flow remains alive, all of its associated tasks will remain alive. Understanding the lifetime of a task is very important because it affects the callable, particularly its captured variables. When the task flow is destroyed, all of its tasks and their captured variables are also destroyed. For example, the code on the lower left can crash because the task flow is destroyed after the block, while the executor may still be running it. So, it is your responsibility to keep relevant task flows alive during the executions. Because the executor does not assume any ownership of a graph, you should never modify a graph during its execution. Doing so can result in undefined behavior such as data race, program crash, unpredictable results, and so on and so forth. For example, the code on the lower left may crash because the graph may still be running while you want to modify it. To fix the problem, we need to wait for the task flow to finish before we want to modify it, as shown on the right side of the slide. All the execution methods in Executor are thread safe. It is completely safe to issue multiple submissions from different threads, and these threads can be either internal to the executor or external to it, such as a freelancing thread. For example, in the code below, I have 100 threads, each randomly submitting one task flow out of 10. Although we can do this, we should be aware of that the execution order of different task flows submitted by different threads is non-deterministic, while multiple submissions of the same task flows are still executed sequentially. For example, as you can see from the execution timeline for the code below, there is no particular order in which a task flow will start or finish after its submission, except that the repeated submissions of the same task flow will execute sequentially, that is, task flow number 4. You can query the worker ID from an executor. Each worker in an executor is assigned with an integer ID from 0 to n-1, where n represents the total number of workers you use to construct the executor. You can query the ID of the calling thread specific to the executor by the member function thisWorkerID. If the calling thread is not a worker of the executor, -1 will be returned. For example, the code below creates an executor of 8 workers and calls thisWorkerID from the main thread, which apparently is not part of the executor's worker. As a result, -1 will be returned. This worker ID is very handy for you to establish worker-specific data structures, such as worker local states or caches, that allows us to step away from a globally shared data storage, which typically incurs centralized synchronization overhead. For example, the code below defines a worker-specific data vector of 8 entries, where each of the 8 workers accesses its own entry using its worker ID. Now, we are going to understand another important concept of Executor, the cooperative execution. Cooperative execution is an executor function that blocks the calling worker until a condition occurs while allowing progress. By allowing progress, we mean the worker keeps doing useful work while waiting for the condition to happen, instead of sitting idle, like sleeping or preempted by the operating system. Cooperative execution is particularly useful for avoiding deadlock caused by idling workers. If all workers are preempted by the operating system, no one will be able to run tasks. The executors support 2 major cooperative execution methods, co-run and co-run until. Co-run cooperatively run tasks until the given task flow finishes, while co-run until cooperatively runs tasks until the given condition is met. In the lower left example, I create a task flow of 1,000 tasks, where each task submits a new task flow using non-cooperative execution. When you call wait, there is a very high chance that the operating system will preempt the calling worker until the corresponding task flow finishes. However, if all the workers are preempted by the operating system, no tasks will be able to run, leading to deadlock. To avoid this problem, we should use co-run, as shown on the lower right, to enable cooperative execution on these 1,000 task flows, allowing workers to continue performing useful work cooperatively through work stealing. To get a clear picture of cooperative execution, let's visualize the previous example. Here, the left visualizes the non-cooperative execution and the right visualizes the cooperative execution. Without cooperative execution, after you submit a task flow from a worker, that worker is blocked at the wait call and makes no further progress. Eventually, no workers are available in the executor. On the other hand, with co-run or cooperative execution, the worker waits for the task flow to finish, but still cooperatively helps execute tasks with other workers. So, it is very important to understand the difference between non-cooperative execution and cooperative execution, and use them correctly in your application. Basically, non-cooperative execution can block workers and cause deadlock, while cooperative execution lets the worker continue processing tasks while waiting. You can perform cooperative execution with a custom condition. Similar to co-run, the function co-run-until provides a more generalized interface that blocks the calling worker until the given condition is met, while allowing the worker to continue running tasks through its work-stealing loop. Like this, co-run-until allows you to specify an arbitrary condition that decides when to stop cooperative execution, which is especially useful for implementing custom synchronization or pooling strategies. For example, the code below launches a standard asynchronous task from a Taskflow task, and then uses co-run-until to cooperatively block the calling worker until the future is ready. Now, we are going to understand how to observe and customize worker behavior in the executor. To observe worker activities, Taskflow provides an interface class, observer interface, with a set of virtual methods for you to override so you can define callbacks for setting up the observer, recording before and after a task finishes. These virtual methods are setup, onEntry, and onExit. Setup will be called by the executor once when the observer is constructed, and it will receive the number of workers as an input argument. OnEntry will be called by the executor before a worker begins to run a task. OnExit, on the other hand, will be called by the executor after a worker finishes executing a task. Here, worker view and task view are just lightweight wrapper over the observing worker and task, which can be used to query the worker's ID, the task's names, and so on and so forth. And the reason for these lightweight immutable wrappers is that we would like to prevent users from directly or accidentally modifying the underlying worker and task storage, which could lead to undefined behavior in scheduling. This slide shows you an example of how to derive a custom observer from observer interface. The constructor takes a string that represents the name of the observer. The setup function prints the number of workers provided by the executor, while onEntry and onExit prints the worker ID and the task's name. Next, you can create an observer from the derived class by calling the executor's makeObserver function. In the example below, we create a myObserver with the name OBS and obtain a shared pointer to it. Internally, the executor keeps a shared ownership of each created observer because it needs to ensure that the observer remains alive while the executor may call its virtual methods. If you no longer need an observer, you can remove it from the executor using the function removeObserver. This is the sample output from the previous slide. We will first see the name printed by the constructor of the observer and then the message from the setup method. Then, when the executor starts running the task flow, we will see the message of which worker runs which task. For example, worker 2 ready to run A, the message from A, and worker 2 finish running A, and so on and so forth. Based on this observer interface, we have implemented a default observer called TFProf, which allows you to visualize execution of your Taskflow programs in the browser interface by running your program with the environment variable TF-enable-provider enabled. Then, you can paste the output of the JSON content to our visualizer at taskflow.github.io/tfprof. Visualization helps you understand how tasks are scheduled and executed across different threads, making it easier for you to analyze and optimize the performance of a Taskflow program. If you don't want any visualization, but some simple summary about the execution statistics of your Taskflow program, you can enable the environment variable TF-enable-provider with an empty string. When you do this, Taskflow will simply print a concise execution report directly to the console. The report has two main sections, task summary and worker summary. In a task summary, for each task type, you will see how many times the task run, total time spent on the task, average execution time per task, min-max representing the shortest and longest execution time among all tasks. On the other hand, in the worker summary, it shows you similar statistics for each worker, giving you a sense of how tasks are distributed and executed across different workers. You can configure the worker property using the interface class worker interface, which provides a set of callbacks for you to modify the worker property. The class has two important methods, scheduler prolog and scheduler epilogue, which will be invoked during the construction of an executor before and after the scheduler starts and finishes. For example, here we create an executor of 4 workers and configure each worker's behavior through the helper function makeWorker interface, which instantiates the custom worker behavior class derived from worker interface. Most applications leverage worker interface to assign a worker to a specific CPU core so they can improve cache locality and reduce context switch overhead. Keep in mind, both prolog and epilogue function can be invoked simultaneously. It is your responsibility to ensure no data race can happen during their executions. This diagram shows a high-level picture of how worker interface fits into the execution flow. When you create an executor, the constructor will start by creating a number of worker threads. For each worker, we spawn a thread and immediately call scheduler prolog. Scheduler prolog is the hook that lets the user customize what happens right before a worker enters the scheduling loop. The entire loop is wrapped in a try-catch block. If anything thrown inside the scheduling loop, we capture the exception in the per-thread variable exception PTR. Finally, when the loop exits, we call scheduler epilogue on worker and the exception PTR. So, scheduler epilogue is the cleanup hook. It lets the user perform post-scheduling work right after a worker leaves the scheduling loop. In today's presentation, we have learned the basic usage of Taskflow Executor and understood how to perform cooperative execution within the executor. Then, we discussed how to define your own classes to observe and customize worker behavior in the executor. If you are interested in learning more about Taskflow, please check out our project website at taskflow.github.io. You can post your questions on the issue page of our GitHub repository. With that, I'm going to stop here. Thank you very much.